today's topic is time-like congruence. It is related to the geodesic congruence and Raychoudhury's equation. So let us study a fluid made of particles which move along a set of time-like curve with a velocity specified this. It is some velocity field. Okay, so we are considering a study of the fluid made of particle which move along a set of time-like curve with a velocity this. We will call this set of curve as a congruence in a particular region of space-time. If there is only one curve passing through each event in the region, congruence can be defined more precisely, but this is adequate for our purpose. If all the curves in the congruence are geodesic, we call it is a geodesic congruence. Okay. The deviation vector eta between any two particles traveling along any two curve in this congruence is parallel transported along the congruence and will satisfy the condition this. Okay. And this implies that UB delta B epsilon or eta A is equal to eta B UA is equal to eta B QAB, where this indices A, B or I, this refers 0, 1, 2, 3, 4. 0, 1, 2, 3. So instead of Greek indices, we are using Latin indices, okay, for the space time. So this equation, this Lie derivative equation gives us this. So showing that the quantity this QA and QB is nothing but del B UA determines the manner in which spatial separation between nearby particles change with time as a fluid moves. The fact that UA and UA is equal to a constant implies that UA QAB will be 0. In the case of a geodesic congruence, we also have this UB del B UA is equal to 0, ensuring that UB QAB is 0. So in the rest frame of the fluid element in a geodesic congruence, this tensor QAB is purely spatial. Okay. For many applications, it is convenient to rewrite del J UI by the following procedure. First, we will separate out from del J UI the part AI UJ, where AI is the acceleration vector. This is the acceleration vector. This is convenient since this term will vanish for a geodesic congruence, which is what we will deal with the most of the time. The remaining second rank tensor can be separated out into a symmetric and antisymmetric parts. The symmetric part can be further split into the trace term proportional to the del ij and the trace part. For our purpose, it is also convenient to concentrate on all the physical quantity projected onto the 3 space orthogonal to ui. So del j ui is equal to this omega ij plus sigma ij plus 1 by 3 theta pij minus ai uj, where pij is nothing but del ij plus uj uy uj is a projection tensor and ai is equal to uj del j ui is the acceleration of the fluid. Okay, so it is the expression of the fluid, it is a projection tensor. And theta, which is del I ui, is the expansion, and omega ij is the rotation. So we classified this del j ui in the rotation, expansion, acceleration, etc. Okay, and see, sigma ij is shear. So we can write down omega ij as 1 by 2. Please mention this Latin indices refers to the Greek indices, means 0, 1, 2, 3. ui minus pim del m uj, and sigma ij, which is shear, is 1 by 2 pmj del m ui plus del m I del m uj minus 1 by 3 theta pij. Okay, so expansions is involved in the shear. There is a negative sign of the expansion in the shear. From the definition, it is easy to verify the following facts. Number 1, omega ij is antisymmetric, while sigma ij is symmetric and traceless. Both shear and rotation are orthogonal to the 4 velocity ui. Okay, the separation also has another useful feature, and that is the Frobenius theorem for any hypersurface which is orthogonal vector to the field. If the congruence is made of geodesic and ui is the hypersurface orthogonal, one can prove another useful result. Whenever a geodesic congruence is hypersurface orthogonal, it must have omega ab is equal to 0. To prove this, we first note that hypersurface orthogonality implies that vector field has a form this: uix is equal to minus mu del I phi for two functions mu and the phi. From this we have a relation del b ua is equal to minus mu del b del a phi minus del a phi del b mu, which implies that omega ab is equal to minus del a phi del b mu in this equation, and we get the condition del a mu is equal to ua ub del b mu. Substituting this back into the expression for omega ab, we find that it vanishes identically for geodesic congruence. But all these quantities, expansion, shear and rotation, will involve as the fluid moves through space-time. We will find that it is particularly useful to follow the evolution of theta. So we want to obtain an equation determining how the expansion theta for the congruence change along the flow lines. To keep it general, we shall assume that the flow lines are made of arbitrary time-like curves which are not necessarily geodesic, and direct differentiation of theta gives this: ub del a del b ua minus rbc ub uc. Okay, and we can further write down this ua ub del a del b ua, okay, in terms of the rotation tensor. Okay, so after some mathematical jugglery, we can find out this d theta over d tau is del a plus 2 omega square minus 2 sigma square minus 1 by 3 theta square minus r a b u a u b, and it is nothing but it is a very famous Raychoudhury equation. Okay, and we can write down it is in this way: minus 1 by 3 theta square plus 2 omega square minus 2 sigma square minus RAB UA UB. Okay, as this is 0. So it is a nothing but very famous Raychoudhury equation.